In our first example for section 3.2, we're going to use the definition of derivative of a complex function. And as a reminder, that definition is to compute the derivative at z0. You take the limit as delta z goes to 0, f of z0 plus delta z minus f of z0 over delta z. That should look familiar from calculus. We're going to learn that since our complex numbers divide, well, first of all, we can divide by complex numbers, but somehow there's sort of two real dimensions we're dividing by. And this is going to allow for a lot of interesting things to happen for differentiability and complex numbers. So anyways, this is where, in my opinion, the course starts getting very, very exciting. So what we're going to do is we're going to look at the function f of z is z squared minus 5z. And we're going to use our definition, and we're just going to compute from that definition f prime of z naught. Just a reminder on how these computations work. These computations shouldn't be new in any way. So we're going to look at the limit as z goes to z naught, and then we'll plug z naught plus delta z into our function. Oops, shoot. Delta z goes to 0, my bad. And then we're going to plug in z naught plus delta z into the function. That's the first step. All right, this part is our f of z naught plus delta z part. All of that. And from that, we're going to subtract off f of z naught. We should be careful with our parentheses. This is f of z naught. Fantastic. And then we're going to go in and we're going to divide by delta z. Now, if you remember these computations, you know that the setup is usually kind of involved. Once you start multiplying stuff out, a lot of things cancel. So let's go and multiply it out. So if we square this binomial expression, we get z naught squared plus 2 delta z z naught plus delta z squared. And then move the minus 5 in. So it's minus 5 z naught minus 5 delta z. And then move the negative sign in. So it's negative z naught squared plus 5 z naught. And that's all over delta z. Again, there's a lot going on, but if you remember, in these computations, a lot of stuff cancels. So let's see, our plus 5z naught cancels with that negative 5z naught. Our z naught squared cancels with that negative z naught squared. And then I think that's it. So let's rewrite this now that we have 4 less terms. We have, let's see, we have a delta z squared, and then we have a 2 delta z z naught, and then we have a minus 5 delta z, and that's all over delta z. So now we do some algebra to simplify our limits. There's a delta z in every term, so we can cancel out 1 delta z in every term, and we're left with the limit as delta z goes to 0, delta z plus 2z naught minus 5. Now as delta z goes to 0, only the first term has a delta z, so we just plug in 0 there. So we're left with 2z naught minus 5. So let's go up and let's see if this agrees with what we know happens with derivatives. So f of z is z squared minus 5z. If we were to pretend like the normal rules from calculus of a real variable apply, you'd bring down the 2 and then get rid of the z for 2z minus 5. That's exactly what we found. Fantastic. So f prime of z naught is in fact 2z naught minus 5, and we've verified a differentiation rule in this special case of a quadratic function.